Hello students, today we're going to look at how to find all the roots of a polynomial equation or polynomial function. Remember,
This is sick lady down for the last lady.
Oh.
She's soft.
Oh, okay. All
Don't
right.
stop it. I'm trying to keep going.
Okay.
I'm
Let's
ready
start
to
again.
line up 30 coins. So.
Counting down to 3, 2, 1.
hello students, today we're going to look at how to find all the roots of a polynomial equation. Remember, any polynomial function not only going to have real roots, but also maybe they have imaginary roots. So the question that we have in here is, the function that we have in here is 2x4 plus 3x cubed minus 3x squared plus 3x minus 5. First of all, we have to take a look at the degree of the polynomial. Remember, the degree of the polynomial is going to be the highest exponent or the biggest exponent I can see. So the degree of this polynomial is 4. Because the degree is 4, we have at most, we have the maximum number of 4 0, excuse me, because the degree of the polynomial is 4, we have 4 zeros. Now, we're going to use the Descartes' rule of sign to make the decision how many of those 4 rules going to be positive and how many of those 4 rules going to be negative. Remember, for looking at the positive real zeros, we're going to look at the function f of x. So I'm going to rewrite the function 2x4 plus 3x cubed minus 3x squared plus 3x minus 5. Now, I'm going to take a look at the coefficient that I have in here and see how many change of the sign I have in a coefficient. The first coefficient is positive 2. The second one is positive 3, so I didn't have any change. Both of them are positive. But the next coefficient is negative 3. So in here, I have one change in the sign. Then again, from negative 3, the next coefficient is 3. So here is a negative number, here is a positive number. I have another change of sign in here. Also from positive 3, the next coefficient is negative 5. In here I have positive, in here I have negative. So I have another change in the sign. In total, I have 3 change in a sign. That means I have 3 positive zeros. So from that 4 0, 3 of them are positive. Now, for finding out how many negative I have, I can take a look at the f of negative x. Now, instead of x, I'm going to plug in negative x. So I have 2 negative x to the power of 4 plus 3 negative x to the power of 3 minus 3 negative x squared plus 3 multiple with negative x minus 5. So now, if I write down this, negative x to the power of 4 is just going to be x4. Remember, whenever the exponent or the power is positive, the sign is going to be positive. So I have 2x4 minus 3x cubed. Negative x squared is just going to be x squared. So I have negative 3x squared. Negative x multiple with 3 going to be negative 3x. And I have that negative 5. Now, I'm going to take a look at the change of the sign of the coefficient. The first coefficient is positive 2. And then the next coefficient is negative 3. So in here I have positive, but in here I have negative. The rest of the coefficients are negative, so I don't have any change in the sign of the coefficient. I just have one change in the sign of the coefficient, so I have one negative 0. Okay. The next step is to use rational zero theorem to identify those potential zero. Remember, for the rational zero theorem, we're going to take a look at the leading coefficient which in here our leading coefficient an is 2. Also, we're going to take a look at the constant, or our a0. So in here, our a0 is -5. And then in the next step, we're going to take a look at all the factors, all the leading coefficients. So what are all the factors of 2? All factors of 2. What are those factors? The only number can count 2 is 1 and 2. But remember, we also have positive and -1 and positive and -2. Now, I'm going to take a look at all factors of -5. All the factors of -5 are what? 1 and 5. Also positive -1 and positive -5. So I have all the factors of the leading coefficient, and I have all the factors of the constant. So rational zero theorem states that if I take a look at all the factors of the constant, divide by all the factors of leading coefficient, those are going to give me my potential zeros. So in here, I'm going to have a fraction of plus and minus 1, also plus and minus 5, over plus and minus 1 and plus and minus 2. So all the factors of the coefficient over all the factors of leading coefficient. So now, plus 1 over 1 is 1, and 5 over 1 is 5. So I have plus and minus 1 and plus and minus 5. I also have 5 over 1, and I also have 5 over 2. So 5 over 1 is just 5, but 5 over 2 is just going to give me 5 over 2. But that's going to be both positive and negative. So those are my possible zeros. So I know one of the zeros could be plus and minus 1, plus and minus 5, or plus and minus 2.5, or 5 over 2. There is 2 ways to guess which one of those, how many zeros we have. 6 zeros is going to be our 4 zeros, or maybe we have imaginary 0. So one of them is using the factor theorem, and another way is to use the graphing utility. So you can just go ahead and use graphing calculator to graph the function. So I did that, and it seems that the graph of my function, it has that general form. As you see, it seems that one of the zeros is 1. It seems that the graph is crossing the x-axis at 1, and also somewhere between -2 and -3. So probably one of my zeros is 1, and one of my zeros is -5 over 2. But for checking that, I can use the factor theorem. I can go ahead and just simply plug in 1 into my function. If I plug in 1 into my function and I ended up having 0, that means 1 is one of the zeros. So let's try that. Just plug in 1 instead of x, gonna give us, let's plug in 1 again instead of x. Let's plug in 1 again instead of x. I don't have enough room. I have to put that plus 0 a little bit away. And I have plus 3 multiplied with 1 minus 5. So look, I have 2 plus 3, 5. That's going to cancel out my -5, and -3 and plus 3 is 0. So good thing I got 0. I also can go ahead and just plug in the -5 over 2 into my function. And surprisingly, again, I'm going to get 0 if you just plug it into the function. This is using the factor theorem. But also, let's say we just plugged in 1 and we found that 1 is one of the zeros. We can use the synthetic division to find out the rest of the zeros. So for synthetic division, I'm going to write down all the coefficients in the order. So my coefficients are 2, 3, -3, 3, and -5. Then I know one of my zeros is 1, so I'm going to put that 1 in the box here. So let me just raise my graph here so I have more room to write down the rest of this question. You can use graphing calculator to graph your function to guess about what are those zeros. But if I want to use the synthetic division, I'm going to draw a line. I'm going to leave some room for myself. I'm going to copy the first term, first number. That's going to be 2. Next step is to multiply whatever is in your box with that number. So I'm going to multiply 1 with the 2. That's going to be 2. And I'm going to put it here. Now I'm going to add these two numbers. 3 plus 2 is 5. Again, I multiply 1 with 5. That's going to give me 5. If I add -3 with 5, that's going to give me 2. If I multiply 1 with 2, that's going to be 2. Again, adding these two numbers, 3 and 2, are going to give me 5. Now, if I multiply 1 with the 5, that will be 5. -5 plus 5 is 0. Let's see, the remainder is 0. And those are the coefficients of the depressed equation. So I can see my f of x actually is x minus 1 because 1 is one of the zeros, x minus 1 is one of the factor. And then this is going to be the my function has a degree of 4. So x minus 1 is degree 1. So I have to, the depressed equation going to have degree of 3. So 2 is the coefficient of x cubed. 5 is the coefficient of x squared. 2 is the coefficient of x. And 5 is my constant. Now, from here, I can, as I said, there is different way to deal with that. You could like take a look at the graphing calculator and just plug in, and based on the graph, you can guess what is your next 0 and just put it in the calculator to see if that's going to be 0 or not. Or you can continue factoring the depressed equation. So I want to show you how to continue factoring that. If I just exchange the order of these two, my equation is going to be much nicer. I'm going to have 2x cubed plus 2x. And then I'm going to have 5x squared plus 5. If I just take a look at the first two terms, it seems that in these two terms, they have 2x in common. So I can go ahead and factor out the 2x. If I factor out the 2x from the first term, I'm just going to left with the x squared. And if I factor out the 2x, I'm just going to left with 1. Now, in my second terms, it seems that I have 5 in common. So I can go ahead and factor out the 5. That's going to be x squared plus 1 again. Now, the x squared plus 1 is in common in both of those terms. I can go ahead and factor out that x squared plus 1 from both of those terms. This way, I'm just going to have 2x left for my first term, and I'm just going to have 5 left from the second term. Remember, I also had that x minus 1 in the beginning of my function. So now I factor out my function. Very good. So it's been all factored out. If I want to find the roots, it's just enough to put the f of x equal to 0 and solve. So if I put the whole thing, let me just make some more room here for myself. So if I put the f of x as x minus 1, x squared plus 1, and 2x plus 5 equal to 0, this is a multiplication of 3 terms. That means either of those could be 0. So either x minus 1 is 0 or x squared plus 1 is 0, or 2x squared plus 5 is 0. By solving that, I'm going to get x equal to 1. And by solving that, I'm going to get x equal to negative 5 over 2. But how about this one? How about this middle one? Now, if I subtract both sides of the equation, my x squared is going to be negative 1. But there is no way that a positive number like x squared could be equal to a negative number. That's where the imaginary number are born. Instead of negative 1, I imagine this is going to be equal to an I squared. So now when I take the square root from both sides of the equation, I have x being plus and minus I. So not only one of my root is 1 and the other one is negative 5 over 2, but also I have two imaginary roots which are positive I and negative I. Now, down in here, I'm going to just write down all the solution or the roots in my curly bracket. So one of the root is 1, one of the root is negative 5 over 2, another root is I, and the other one is negative I. So as we wanted, we found all of the roots of that polynomial. 2 of them were real numbers, and 2 other ones are imaginary. So when we graph it, we were just able to saw the real zeros or real root, but we didn't see the imaginary one. I hope that you enjoyed that question. Thank you.